Welcome to this lecture series in linear algebra. In this lecture, we'll look at the notion of a subspace, and let us briefly look at what we have done so far. So we have defined what is a field, and then we defined what are vector spaces. We looked at some examples. So these are our fundamental examples. Mostly for this lecture series, this much is sufficient. We will not be dealing with generally, any other field than real and complex, but everything that can be proven in full generality will be proven in full generality. My point is that for the first course in linear algebra, it is enough to just focus on these two spaces and at max that. But everything that we will do, if it can be proven in full generality, meaning for an arbitrary field, we will prove it for an arbitrary field. So there is no loss. Okay, and then we looked at these examples. Actually, we only looked at this one, but you can easily mimic that example to get all of these things, and in fact this one. So let me not say too much about this because this will be discussed in more detail later. And then we finally looked at some mixed examples where your space is constructed using real numbers, but the base field, this thing is called the base field, is not real. It is something inside the real numbers. And same for all of these examples. Okay, so now let's continue. Here are some two problems for practice. And now let us get started. So before we formally define a subspace, let us at least have some visual cue to guide us to a right definition. So we have this vector space R2, a real vector space. When we say a real vector space, I mean the base field of the vector space is R. So VF plus dot, this vector space is called a real vector space if this guy is the real number field. Okay, so we have R2, which is a real vector space, and we have marked out a subset of R2. So this is meant to be a line extending infinitely in both directions, a line passing through the origin. And one can immediately observe that, or at least feel that, this is just a copy of the real numbers. So the real numbers, which we visualize like this, is a vector space over the field of real numbers. One should be able to see that this thing is just a copy of that, or at least should be able to agree with that statement, even though that formally has not been defined. And to give it a little bit more weight, one can note that if you add two things from this particular subset, you land inside this particular subset. You do not leave it. And if you scale something from this subset, you again remain in this particular subset. So this is closed under scaling and addition. That's how we express it. And therefore, for all intents and purposes, one can treat this as a copy of that. So this is basically the motivating idea. Formal definition will be given. Of course, things will not be clear just by this hand-wavy kind of picture. So here is the thing. Here is how we can make that precise. Fix a vector space V over some field F, and we have a subset of the vector space which is non-empty. Then we say that the subset is a subspace of V if two things happen. One, closure under addition. Which means what? Which means that whenever we pick two things in S, their sum is also in S. So this sum is legitimate. When we say sum, we just mean, this vector space already comes with its plus function. And since anything that is a member of S is also a member of V, it is legitimate to operate the addition function on these two elements. After all, these are vectors in the big vector space V. So closure under addition means this: whenever you pick two things, their sum is also there, and then similarly we have closure under multiplication. Under scaling, I mean, not multiplication, under scaling. So this reads, whenever you pick alpha in the base field and you pick anything in S, you find that the scaled version is also in S. So if these two properties are satisfied, we say that this guy is a subspace of V. And clearly now one can see that if you have a line passing through the origin in R2, then this is a subspace. And a three-dimensional example, we haven't defined dimension, but still I hope you can agree with the phraseology. So we have this R3, this big thing was R2, and here it's difficult to draw, but you can imagine a plane passing through the origin. I don't know how to draw that. So something like that. I mean, my drawing is not great here, but I intend this to mean a plane passing through the origin. So it passes through this point and it's a plane. And this you can verify is also a subspace of R3. So these are two examples. Of course, we'll look at many examples. This will be a frequently recurring notion, a very important one. In fact, in mathematics in general, you have this notion of sub-objects. You have a parent object, and then you have a sub-object sitting inside it of the same kind. Here the kind is vector space, and the sub-object is, of course, a vector space. We will get to that very soon. In fact, this comment is meant to formalize the fact that a subspace is a vector space in its own right. So this notion of sub-objects is very frequent and ubiquitous in all mathematics. Okay, so here is the comment. A subspace is a vector space in its own right. What does that mean? What does this mean? Just give me 1 second. Yeah. So once you have a subspace, we have already defined what is a subspace. So now suppose S is a subspace. So V is a vector space and S is a subspace of it. And where F is the base field, let me not write that. So then what you can do is you can borrow the addition from V and define a new function on S. So define this, which by abuse of notation we are using the same plus as the one here. So this is what we are defining, and we are defining how? Just U comma V going to U plus V, where this plus is borrowed from here. So if you want, you can put a subscript here so that there is no confusion. So this is a new plus or a new function that we define on S, which just borrows from the plus that we have on the parent space. And similarly, we have a scaling function, which I will denote by dot and a subscript S from F cross S to S, which takes a scalar, and so the elements of the base field are also called scalars. A scalar and a vector to that, and here this scaling is happening as if we were a member of the parent space. So this is legitimate. And before we even make this definition, we should say that since S was closed under addition, this is well defined. Whenever you pick two things, a pair of things in S, their sum as taken in the parent space also lies in S. So this is well defined, and by the same comment, this is also well defined. So this can be done only when S is a subspace. Otherwise, one cannot even define these two things. Okay, so these are our addition and scaling functions, and now one can easily check. So I leave that to you. So check that this quadruple is a vector space. So every subspace naturally is a vector space in its own right. And that is what I was blabbering about here, that you have a sub-object sitting inside a big object. Okay, so I don't think there's anything mysterious about any of this. And it's a very beautiful concept. Alright, so let's move on. So subspaces of R. What are all the subspaces of this guy? So we have this vector space. We visualize it like that. So suppose it has a non-zero vector in it. S has a non-zero vector in it. Now, since any subspace is closed under scaling, all scalings of this by real numbers will also be contained in S. and hence everything will be contained in S. Because if you are scaling a non-zero real number by any real number you like, you can achieve any real number you like. So as soon as your subspace has a non-zero element, it has everything. So the only subspace which contains a non-zero element has to be the entire vector space R, and the other subspace would then be just the one which contains only the zero element. So the subspaces of R are this and that. These are the only two subspaces of this guy. Okay, what are the subspaces of R2? So this we will perhaps not do in full detail, but first of all, we should note that any line passing through the origin, if you have a line passing through the origin, that's a subspace. So one subspace is already very clear, this origin. So when I write 0 here, I mean this. So this is a subspace, clearly. This is closed under addition and scaling, no problem. Then you have lines passing through the origin. Every line passing through the origin is a subspace. And of course, we have the entire thing. This is also a subspace. In fact, if V is a vector space, then V is a subspace of the vector space. That's true in full generality. For any vector space, that is true. And similarly, if V is a vector space, then this guy is a subspace of V called the trivial subspace. So these two examples are kind of for free always. So lines passing through the origin are definitely subspaces. Are there any others? And the answer is no. So suppose you have, I'll just argue it somewhat non-rigorously. So suppose you have a subspace which is different from 0. So meaning it has a non-zero vector in it. Okay, so I have a subspace which has, let's say, this vector in it. Since all of its scalings will also be present in the subspace, I already get this entire thing in the subspace. Now there are two possibilities. Either this is the subspace, in which case we have already accounted for it, or there is some point outside this line in the subspace. Well, if that were the case, then first of all of these things will also be in the subspace, because all scalings of that point will be in the subspace. And now, if we pick a point here and a point there, meaning a vector on this line and a vector on this line, and add them, that will also be in the subspace. But if you just think about it, if you choose a point here and choose a point there and add, the set of all such points is everything. You can express everything that way. And therefore, this is a full classification of all the subspaces of R2. So I didn't argue it in full detail, but I hope you can fill in the details. If it is not clear, I would encourage you to stay on this as long as it takes to fully understand why these are the only subspaces. And if you have study groups, you should bounce these things around. Lastly, this is something that I will again not do in any detail. This will be for something for you to think about. What are all the subspaces of R3? I will write down the answer, but then you'll have to justify it. So clearly this is a subspace. Then lines passing through the origin. Planes passing through the origin. And lastly, the entire thing. These are all the subspaces of R3, but you have to prove it. Or at least convince yourself fully. Proof one can, as you learn more and more linear algebra, this will become like a trivial thing. But this should feel right. Shouldn't feel foreign. All right. Another very interesting example of a subspace of Rn. Here we are doing it for Rn, but you can easily mimic this to write down examples of subspaces of Fn. So how do we construct subspaces? Pick n real numbers and define the subset S of Rn as follows. S is defined as those points in Rn such that this sum vanishes. that is S. First of all, this is non-empty because the 0, 0, 0, 0 thing, that thing, is clearly satisfying this equation. So it is a non-empty set. And your job is to check that S is a subspace. Okay. Let me write one more example. Intersection of two subspaces is again a subspace. What does this mean? Let me write it in a more precise fashion. So it says that let U and W be subspaces of a vector space V. Then U intersection W is also a subspace. Okay? And it is immediate from just the definition of a subspace. If you pick two vectors here, let's say X and Y are two elements here, we want to show that X plus Y is also here. How do we do it? Well, if X and Y are here, then in particular X and Y are in U and X and Y are in W. But U is a subspace, therefore X plus Y is in U and X plus Y is in W. But this means that X plus Y is in U intersection W. So you show closure under addition via this simple reasoning, and similarly closure under scaling, and that's it. So intersection of any two subspaces is again a subspace, and therefore you can jazz up this example to create more subspaces. This subspace is obtained by writing one algebraic equation. You can write several algebraic equations and again you will get a subspace. When I say algebraic equations, I mean quote-unquote linear equations. You do not see quadratic terms here. That is important. Okay, lastly, I will just expand on, or maybe I'll call it 5 prime intersection of any family of subspaces, of any collection of subspaces, is again a subspace. So here we made the statement only for two subspaces, but the same can be said for any number of or any collection of subspaces. So if you have a collection of subspaces, if suppose each U alpha is a subspace of some vector space V, so V is a fixed thing and everything here is a subspace of V, then the intersection of all of them is also a subspace of V. Let me write that down. So it means that let V be a vector space and let J be a set, J be a non-empty set, and let U alpha be a subspace of V for each alpha in J. So there is some indexing set, as we call it. For each element here, we have a subspace of V labeled by that element. So it's a collection of subspaces. J could be an infinite set of, or a set of any cardinality, if you know about cardinalities. If you don't, ignore that. So J is just any set, finite, infinite, whatever. And we have a bunch of subspaces indexed by J. Then the intersection of all of them is a subspace of V. The proof is no more complicated than what we saw here, and I leave that to you. Okay, so far, so much for examples. Maybe let us, let me see, what have I said? Okay, so let me delineate two properties of subspaces, and I think, which are here, and I think that will be it. Or maybe there is a little more. So here is a very simple property that subspaces enjoy. We have a vector space over some base field F, and S is a subspace of V. Then the additive identity of V is same as the additive identity of the subspace. So just like in the R2 example, In the R2 example, you take any line passing through the origin. You see the additive identity of this guy is this point, if you just think about it. And of course, the additive identity of the entire R2 is also this point. And this is not a mystery or anything. Basically, you pick, so let V be in the subspace, then 0.V is what? This is going to be, this will lie in S, because all we are doing is we are scaling the vector V by some scalar, which is 0. So it is going to lie in S. But what is this? After all, this scaling is happening in the parent space. So this has to be the additive identity of the vector space V. So at the very least, the additive identity of the parent space lies in the subspace. But it is clear that this behaves as the additive identity of S also, because clearly this plus S is equal to S for all S in S, because this equation is true for all S in the parent. After all, this is the additive identity of the parent. So this is of course true, and hence this is the additive identity of this guy, and we showed that or discussed that the additive identity of a vector space is unique. So this has to be equal to that. As simple as that. I mean, there is nothing, no mystery here. Think about it if it is unclear. A similar comment: fix a vector space over some base field F and a subspace of V, and fix some arbitrary vector in the subspace. Then the additive inverse of V in S. Again, S is a vector space in its own right, so one can talk about the additive inverse of the vector in S or the additive inverse of the vector in the parent space. They are the same things. And I leave the proof to you. Just like here, the proof is going to be very, very simple. Okay. Finally, sums of subspaces. I mean, we could have defined, we could have discussed this in the examples portion, but let's do it separately. So fix a vector space over a field F, and suppose we have two subspaces of the vector space V. Define U plus W as all the vectors of this form, where you pick the first guy from U and the second guy from W. So this plus has again nothing to do with any plus that we have seen before. This is a new thing that we are defining, while this plus is from the vector space V. So this is the definition of sum of U and W, and check that. U plus W is a subspace. Very simple exercise. Okay, so I think this is enough. As usual, like, comment, share, subscribe, and I will see you next time. All right.